Covariant derivative 1. In this chapter, we derive the concept of differentiation in relativity. This chapter is divided into two parts. In general relativity, all equations are required to take the same form in every coordinate system. That is, they must be tensors. This is known as general covariance. The same requirement must apply to the operation of differentiation as well. What kind of differentiation can be applied in both flat and curved space, and always yields a tensor? Deriving this is the theme of this chapter. Let us begin by reviewing the differentiation of vector fields in Euclidean space, which we are familiar with. This represents the rate of change between two infinitesimally separated points x and x plus dx, and is defined as follows. We verify whether ordinary differentiation has tensorial properties. We have a coordinate transformed vector A, prime mu. We differentiate this with respect to x prime nu and examine how it is expressed in the original coordinate system, and whether it takes the form of a tensor. Applying the chain rule to the second term on the right-hand side. The first term appears as an extra term, which shows that ordinary differentiation is not a tensor. This extra term appears regardless of whether the space is flat or curved, which means that ordinary differentiation cannot be used as an operation in relativity. When we extend this to curved space, a new challenge arises. In curved space, the basis vectors differ from point to point. Therefore, even for the same vector field, the components are expressed differently at x and x plus dx, making direct comparison impossible. The ordinary definition cannot be applied. How can we preserve the tensorial property, covariance, in the differentiation of vector fields in Riemannian space? The key is parallel transport. Parallel transport corrects for the shift caused by the difference in basis vectors between x and x plus dx, allowing the value of the vector at x plus dx to be correctly expressed in terms of the basis at x. This follows from the proof that the magnitude of a vector is preserved under parallel transport. Therefore, by taking the limit of the difference between the vector at x plus dx and the parallel transported vector, we can define the correct relativistic derivative in curved space. This is called the covariant derivative. The notation on the left-hand side is the mathematical symbol for the covariant derivative, representing the rate of change of the covariant vector field A mu as it moves along x nu. We substitute the parallel transport formula into the definition of the covariant derivative. The term on the left is the definition of the ordinary partial derivative, and the deltas on the right reduce to the Kronecker delta. Therefore, this is the relativistic derivative, the covariant derivative of a covariant vector field. The Christoffel symbols correct for the change in basis vectors in curved space. In flat Euclidean space with a Cartesian coordinate system, the Christoffel symbol terms vanish, and the covariant derivative reduces to the ordinary partial derivative of the vector field. We have derived the covariant derivative of a relativistic vector field. As a special case, let us examine the covariant derivative of a vector under parallel transport. In general, a vector field does not necessarily become zero in either Euclidean or Riemannian space. However, in the case of parallel transport, the vector is invariant, and therefore both the ordinary derivative and the covariant derivative become zero. We can say that parallel transport is the motion that makes the covariant derivative zero in curved space. But does this have any meaning? It does. First, this leads to the geodesic equation. The path that moves straight through curved spacetime while preserving the magnitude and direction of the vector. Second, while we have shown that the change in vector a mu parallel transported along a single path x nu is zero, in curved space the result of parallel transport along different paths does not become zero. And this reveals the essential existence of curvature. These are what connect to Einstein's gravitational equation, which states that the cause of gravity is the distortion of spacetime. We will deal with this in detail in later chapters. Tensorial property of the covariant derivative, covariant vectors. We have derived the covariant derivative of covariant vectors in curved spacetime. Now let's verify that this is indeed a tensor. We begin with the covariant derivative under coordinate transformation. The ordinary derivative is given by this expression. Where the first term on the right is the extra term. That prevents ordinary differentiation from being a tensor. Substituting this into equation star. Substituting the transformation laws for the Christoffel symbols. And the covariant vector A prime lambda. Feel free to pause and follow the calculation at your own pace. We expand and simplify, applying the Kronecker delta and relabeling dummy indices. The extra terms cancel each other out. Let's collect the remaining terms by their common factor. The expression in the parentheses is the covariant derivative. We have confirmed that the covariant derivative of covariant vectors is a tensor. We have derived the covariant derivative of a covariant vector and confirmed that it transforms as a tensor. The left-hand side has two covariant, lower, indices. And on the right-hand side, the transformation law for covariant vectors partial x over partial x prime appears twice. This confirms that the covariant derivative of a mu with respect to x nu transforms as a 0 2 tensor. Note that an ordinary derivative does not transform as a tensor. Only the covariant derivative transforms covariantly, making it the correct differential operation that maps tensors to tensors. This is the essential beauty of the covariant derivative. The covariant derivative, being a tensor, describes the same physics regardless of the coordinate system. This is the unique differential operation that satisfies Einstein's requirement in general relativity. The equations of physics must take the same form in all coordinate systems. Covariant derivative of contravariant vectors. Similarly, for contravariant vectors, we take the limit of the difference between the vector at x plus dx and the vector parallel transported to x plus dx. We substitute the parallel transport formula for a contravariant vector. This gives the covariant derivative of the contravariant vector. Proof that the covariant derivative of contravariant vectors is a tensor. We begin with the equation under coordinate transformation. We differentiate the transformation formula for contravariant vectors with respect to x nu. To replace the red term, we differentiate both sides of the Kronecker delta identity with respect to x alpha. The following slides contain a detailed calculation proving that the covariant derivative of a contravariant vector transforms as a tensor. Please feel free to pause and verify each step at your own pace. Here, we relabel the dummy indices of the term marked in red, the term we wish to eliminate, to match the extra term in the coordinate transformation law of the Christoffel symbol. By aligning these indices, the unwanted term coincides with the extra term in the Christoffel symbol transformation law, which leads to the proof of the tensorial property, as we will confirm in the following slides. We have derived the covariant derivative of a contravariant vector and confirmed that it transforms as a tensor. The left-hand side has one covariant, lower index, and one contravariant, upper index. On the right-hand side, the transformation law for contravariant vectors partial x prime over partial x appears once, and the transformation law for covariant vectors partial x over partial x prime appears once. This confirms that the covariant derivative of the contravariant vector a superscript mu with respect to x nu transforms as a 1 tensor. The covariant derivative maps a contravariant vector to a 1 tensor, transforming it correctly as a tensor. Covariant derivative of tensors. Let's derive the covariant derivative for tensors of rank 2 or higher. We begin with mixed tensors. To derive the covariant derivative, we first consider the parallel transport of tensors. Let's verify how the product of contravariant and covariant vectors transforms. Transformation law for contravariant vectors. Transformation law for covariant vectors. We form the product A prime mu b prime nu of a contravariant and a covariant vector. This shows that the product transforms as a 1 tensor. We denote this mixed tensor by T superscript mu subscript nu. The product of the transformation laws for a contravariant vector and a covariant vector satisfies the transformation law of a mixed tensor. From this, when deriving the covariant derivative of a mixed tensor, it is natural to define the parallel transport of the tensor as the product of the parallel transport of the contravariant vector and the parallel transport of the covariant vector. We have seen that the parallel transport of a mixed tensor is naturally defined as the product of the parallel transports of its component vectors. This suggests a second natural requirement. Since a mixed tensor can be expressed as a product of vectors, its covariant derivative should satisfy the Leibniz rule. Therefore, we derive the covariant derivative of a tensor from the following two requirements. The product of the parallel transports of a contravariant vector and a covariant vector gives the parallel transport of the tensor. For a mixed tensor expressed as the product of two vectors, the Leibniz rule holds for the covariant derivative. We confirm that these two requirements lead to the same expression and define it as the covariant derivative of the tensor. From requirement 1, we form the product of the parallel transport of the contravariant vector and the parallel transport of the covariant vector. We neglect terms of second order in delta x sigma. Thus we obtain the equation for the parallel transport of a mixed tensor. We substitute this into the definition of the covariant derivative. This is the expression for the covariant derivative of a mixed tensor derived from requirement 1. From requirement 2. The derivative of a product of ordinary functions is given by if the Leibniz rule holds for the covariant derivative we obtain. The expressions A and B derived from requirement 1 and 2 agree. From the above, we define the covariant derivative of a second-rank mixed tensor by the following equation. Proof of the tensor nature of the covariant derivative of a mixed tensor. The expression we have just derived is merely a candidate formula, obtained from two natural requirements. 1. The product of parallel transports, and 2. The Leibniz rule. This alone does not yet constitute a proof. To confirm that this expression actually transforms as a tensor, we must verify that it satisfies the coordinate transformation law. Since it is the transformation law that determines whether an object is a tensor, we now prove this explicitly. We express the covariant derivative of the mixed tensor in the primed coordinate system, and find the coordinate transformed form of each term on the right-hand side. The mixed tensor was defined as the product of a contravariant and a covariant vector. We differentiate T prime mu nu with respect to x prime rho. Applying the Leibniz rule. We find the coordinate transformation of the second term on the right-hand side. The product of the Christoffel symbol and the mixed tensor. We find the coordinate transformation of the third term on the right-hand side. The product of the Christoffel symbol and the mixed tensor. We now have all the terms on the right-hand side. In the next step, we write them all out explicitly. We now write out all the terms on the right-hand side explicitly. This expression contains many terms, so please pause here and take your time to verify each one. Here we relabel the dummy indices to prepare for combining terms later. We also note that the second term and the seventh term cancel each other due to the relabeling of dummy indices. The expression now reduces to 5 terms. In the next step we prove that the extra terms, the first term and the fourth term, cancel each other. We now prove that the first and fourth terms cancel each other. Please pause here and verify each step at your own pace. The first and fourth terms cancel each other. The remaining 3 terms are we rearrange the partial derivatives and factor out the common terms. The expression in parentheses is precisely the definition of the covariant derivative of the mixed tensor. Substituting. The tensor nature of the covariant derivative of a mixed tensor has been proved. The left-hand side has 1 contravariant, upper, index and 2 covariant, lower, indices. On the right-hand side, the transformation law for contravariant vectors partial x prime over partial x appears once, and the transformation law for covariant vectors partial x over partial x prime appears twice. This confirms that nabla subscript rho t superscript mu subscript nu transforms as a 1, 2 tensor. The covariant derivative maps a mixed tensor to a 1, 2 tensor, transforming it correctly as a tensor.